Hi, this is my video number 2. So I'll talk on the double integral of the type 2 region. Yeah, double integral with type 2 region. It's not well focused. Yep. Okay. So double integral with type 2 region. So type 2 region is that we consider the region where, let's say a region D, where xy, all point xy is such that y bounded by two constant C and D, and H bounded by two curves. Let's say H1 y and H2 y. Yeah. So example or sketch of this, for example, if you have a function like this, yeah, this is x equal to H1y, x equal to H2y, and y between C and D. So this is our region. Yeah, this is D. Of course, you can interchange between type 1 and type 2 depend on which one is much easier to do. Yeah? So in this case, our double integral over the region D of function fxy dA, we can write this as a y from C to D. Remember that the outer integral, the limit must be a constant to a constant, C to D, and x from H1y to H2y, f xy dx dy. Let's say example of this. Let's say we have we want to find a volume. Yeah, find the volume. Find the volume of the parabola. Let's say z equal to x squared plus y squared, bounded by y equal to 2x and y equal to x squared. So if we can sketch this, you know, for the surface, we don't really care how does the surface look like, but the most important thing is the region bounded by y equal to 2x and y equal to 2y, because those region, when we project it onto xy, definitely will be bounded by that two function. Okay, so for x and y, just look at those region x and y. Okay, so we have y equal to 2x is let's say this is the y equal to 2x, and y equal to x squared is something like, you can sketch those as that. So our region given is, this is our region, this is y equal to x squared. Of course, you can find the point of intersection there. It's not difficult to do. You have x squared minus 2x equal to 0. So you have x minus 2x, 0. So x equal to 0 and 2. So we have here, this is 2, this is 0, and x equal to 2. If you substitute there, you got y equal to 4. So the point here is 2, 4. So this integral, we want to find the volume of those. So this integral, this our fxy, our function. Okay, so to find the volume, we integrate over those region D. This is our D. Okay, So our fx is x squared plus y squared, x squared plus y squared dA. This will give us, first I will look at the region in the first type, and then we try to look at a region for the second type. Okay, for the first type region we have x from 0 to 2 and y. Okay, if you look at the x, so the smallest for this is that as compared to that one. Okay, smallest means we look at the area under the curve, which one is the smaller. So x squared to 2x, and if xy is x squared plus y squared. In this case we integrate respect to y first, then x. Okay, so integrate this iteratedly. So what we have, integrate x equal to 0 to 2 and y x squared y plus y cubed over 3 d y from x squared to 2x dx. Okay, so what we have, this x equal to 0 to 2, you substitute there, you have x squared 2x plus 2x cubed over 3 minus x squared, you have x squared 2x plus x squared, okay, plus x squared cube over 3, this thing dx. Okay, so simplify this, we have x equal to 0 to 2, this one is 2x cubed, this one you have plus 2a cubed over 3, that one you have minus 2x cubed, this is 2x, yeah. Oh no, this is x squared, sorry. This is x squared, so we have x squared, so we have x quad, that you got minus, you have x 6 over 3 dx. Okay, then from that is not difficult for you to solve this problem. You can do this. The answer is 216 over 3. Now if you want to consider the type 2 region, we have the same region there, but we consider type 2 region, where for the type 2 region we project those region on the on the y axis. Yeah, project on the y axis, so which means we have the outer integral is respect to y, the outer integral respect to y. So let's do this. So our volume, we integrate over a over region D. Function is x squared plus y squared dA. Now consider the type 2 region, where we project those on the y-axis. So what we have, y from 0 to 4, okay, y from 0 to 4, but our x is, so look at x, we need to change those to the x function. So if I do this, so from y equal to 2x, we have x equal to y over 2. And the other one is y equal to x squared, so x equal to plus minus square root y. Of course, the negative side is that part. We don't consider the negative, we can consider only the positive part. So which means our integral, our limit of integration for x is from that line to that line. Okay, so now for this two curve here, all right, the smaller between these two is that one, x equal to y over 2. So we integrate those things, x from y over 2 to z y. Okay, and then those inside there just same the x, then we integrate respect to first we integrate respect to x, and then we integrate respect to y. Do this iterately, so what we have, you will get the final answer the same as the 216 over 35. So give you same answer. Okay, so that's the example of the type 1 and type 2 region for the double integral. Of course, there are some activity, some exercise in your notes. You can try that. Yeah, it's an exercise. You can consider. We evaluate d xy dA, where D is a region bounded by line y x minus 1 and a parabolic y squared equal to 2x minus 6. So I think for this case, this is I guess if you evaluate this whereas using a type 2 region, much easier to solve rather than type 1. Because if you use type 1, you need to write y as a square root of 2x plus 6. Yeah. Alright, and then number 2, if we integrate over, I think this one is much easier. 2x squared minus 3y dA, where your r is given by y equal to x, y equal to 2x, x equal to 0, and x equal to 4. And number 3 again, we evaluate y from 0 to pi, x from 0 to y squared sine x over y dx dy. This is more straightforward. Okay, so we look at the couple of the properties of the double integral. Properties of double integral. Okay, first one is that it is obvious we have, if you integrate over the region D of two functions, over the region D, f xy plus g xy, dA, that give you, we can split this into two. Integrate d f xy dA plus integrate over d g xy over dA. Okay, and number 2, we integrate d for any constant c f xy dA. This is, you can just take out c, then integrate over d f xy dA. for any c a constant. Alright, and if you have a function f xy greater than g xy for all xy in D, then we have integrate over df xy dA. This will be greater than integrate d g xy dA. And number three, so if D is the combination of two regions, D1, D2, and they don't overlap except probably at the boundary, then in this case I would say with D1, D2 is empty. Okay, it's an empty set. Then to find the double integral over region D of any function x, y, dA, you can split those regions into two. D1 fxy dA plus D2 fxy dA. So all these properties actually we have considered in our example. The typical case is that if we have for double integral df xy dA, if our function f xy equal to 1, we know that this integral will give you volume, but for the case of f equal to 1, so what we have, those integral d over region D, f is equal to 1, so we have 1 there, dA, this just gives the area covered by that region, okay? Area of the region D. This I would say area bounded by region D. And finally, if you combine the properties that are given earlier, we have, so that's I have 1, 2, 3, 4, now number 5 here, and number 6, properties number 6, we have, if we have some constant m less than f xy and greater than some constant m for all xy in the region D, then we have m area of D less than, if we integrate over region D, f xy dA less than m a of D. Okay. Okay. For this case, if you can describe this function, it is not difficult to look at. You just consider in 3 dimensions because fxy is our function, our surface. So if this is our surface here, let's say this is z equal to fxy, and we have z equal to m and z equal to, which is smaller than fxy, so which means we have some sort of plane down here, and this is z equal to constant m, and we have another plane up here. This is z equal to capital M. So obviously in this case the surface lie in between plane z equal to m and z equal to capital M. So obviously it satisfies that inequalities. Okay, so with those 6 properties of the double integral, I leave it to you to study those things. All right, next we look at the double integral in polar coordinates. Yeah, so double integral in polar coordinates. So first of all, let me give you what is the polar coordinates. So yeah, what is polar coordinates? So double integral in polar coordinate. The general properties or the principle of how to work on the polar coordinate is exactly the same as what I've discussed at the beginning, where we chunk or we split the small interval into n equidistant sub-interval of the region, of the given region D or R. Okay, but I just want to look at in this case to introduce what is a polar coordinate. You know this polar coordinate. So basically it's still on xy plane, xy plane, but for the polar coordinate we consider any point on the xy plane as the combination of angle and the radius of a circle. Okay, so if you consider that circle, yeah, any circle, let's say x squared plus y squared equal to z squared, sorry, equal to z squared, equal to some r squared, say. So which means our radius here is r and bounded by and angle theta. So this point here, where point xy, we can write in term of polar coordinate r and theta. So the representation of x and y given as x equal to r cos theta and y equal to r sin theta. So the easiest way to look at this thing is that we may consider any point xy in rectangular coordinates. Yeah, any point xy in rectangular coordinate. This is rectangular coordinate. We have a point xy here. We have point xy anywhere on the polar coordinates. You consider that as we transform. Okay, we transform those point xy in rectangular coordinates to the r theta of the polar coordinates. So to do those transformation, the involved is this: x equal to r cos theta and r sin theta. So remember that in the polar coordinates, for the double integral of a region D f xy dA, we can specify what is x, what is y, the limit of the integration, and then fxy, and for this dA we have dy, in this case we have dy dx. Now when we do the transformation, yeah, with those transformation, we're going to have, instead of x and y, now we transform into r and theta. Okay, the function here, instead of function f, x and y, we transform those x with r and theta. So we have r cos theta, y is r sin theta, and of course here we have dr d theta. Oh, I don't have space, so let me write it here, dr d theta. But due to the transformation, we need some more, or one more terms here. what we call as the Jacobian of the transformation. Yeah, Jacobian of the transformation. Now, how to find the Jacobian of those transformation? The Jacobian is given as Jacobian. Let me write as J the Jacobian for this transformation. X equal to arc cos theta, y equal to arc sin theta. Given as we have differentiate respect to r, we differentiate respect to theta, y with respect to r, and y with respect to theta. So if you do this, so what we have now is, this is the determinant of matrix 2 by 2 matrix. So we differentiate respect to x, that give you cos theta. Differentiate respect to theta, that give you negative sin theta, negative arc sin theta. Okay, and then for y, we have differentiate respect to x, we give you sin theta. And if you differentiate respect to theta, that give you arc cos theta. Okay, if you simplify those, what we have, this is arc cos squared theta, minus, you got minus there, so plus arc sin squared theta, that give you arc cos theta squared plus sin squared theta, that give you arc. Therefore, our integral here, d over region D f xy dA, when we transform into the polar coordinates, so what we have is that this is with respect to r and theta. Okay, so our function f is r, x is r cos theta, our y is r sin theta, our dA, so what we have is dx dy, now transform into dr d theta, but we have that Jacobian. In this case, we have r here. So do not forget this r. This r is important. Yeah, if you do this the transformation using a polar coordinate, we have the Jacobian, which is r. So do not forget those r. So if I have example, so let's see, just give me a second. Okay, so let's say example. Okay, before that, so now the transformation now, our region D now, yeah, from this region D, xy, where for x between some a and b, for example, and y between, you can consider g1, x, g2, x, we transform this into r and theta, where r between radius of two circle, I would say, what we call those things, I cannot recall that word, annulus, yeah, annulus, r between a and b, and theta between, let's say, between two angle, yeah, between two angle. So it's depend, I would say, let's say alpha 1 and alpha 2. Okay, so what happened here is that from those region, for example, A and B, this is g1x, y equal to g1x, this is y equal to g2x. We transform this into polar coordinates with something like a circle like this, where this is AB, so those radius A, and the other one is B, and the angle that I say alpha 1 and that alpha 2, and okay, so we have alpha 1 and alpha 2, so our region becomes that. Okay, now let's see example. Let's say we want to evaluate, we have region R, which is, the function is 3x plus 4y squared dA, yeah, where R is the region or bounded by upper half plane, yeah, in the upper half plane. So bounded by the circle x squared plus y squared equal to 4 equal to 1, and x squared plus y squared equal to 4. If you look at these two circle here, this circle with radius 1, this circle with radius 2. Alright, so what we have for those, we have x and y, x squared y squared equal to 1, so let's say that circle, and the other one, this is 1, and the other one is circle with radius 2, so let's say we have those, so this is 2. So now our region is given by that. So basically it's entire circle. So in this case, our theta limit of integration is from 0. Remember that the angle we measure from the x-axis positive and counterclockwise. So the angle is from 0 here, from x-axis, counterclockwise onto that, again to the x-axis, so we got 2 pi. Okay, and the radius is from 1 and 2, so the integral becomes we integrate over R 3x plus 4y squared dA, that squared, equal to, we have, you can put either R first, or you can evaluate theta as depend on which one is easiest to do it. So if you consider theta as an outer integral, then theta 0 to 2 pi, R from 1 to 2, okay, R from 1 to 2, and our function now, we have 3x, our x is R cos theta, okay, and plus 4y squared. 4y squared is, we have 4r squared sine squared theta d theta. Sorry, here we have, remember that for dx dy we have r dr d theta. The Jacobian, do not forget with that. So if you simplify those terms, we have theta from 0 to 2 pi, r from 1 to 2, so we have 3r squared cos theta, plus we have 4r cubed sine squared theta. Alright, so that one we have multiplied inside, so we have dr d theta. Okay, and then we just integrate with respect to r, so what that gives you, theta from 0 to 2 pi, our r is so we have 3r cubed, cancel with 3, so we have r cubed cos theta. That one we have r quad divided by 4, so we have r quad sine squared theta, where r from 1 to 2 d theta. Then this is not difficult to do that. What we have theta from 0 to 2 pi, so you substitute that, you got 8 cos theta, 8 cos theta minus 1, so you 1 cos theta, so that gives you 7 cos theta, and then those you got 16 sine theta, and minus 1 sine squared theta, that gives you 15 sine squared theta d theta. Yeah. Now for this integral, of course, you can split that one by one if you want. That give you 7 sine theta, theta from 0 to 2 pi, plus that one 15, we integrate theta 0 to 2 pi sine squared theta d theta. Okay, so do not take this for granted. Yeah, many students will do this when you integrate respect to a trigonometric series. Just do as a normal. You just sine cube theta over 3. So this is wrong. Don't do this. Okay, don't do this. You need to use the appropriate identity. So in this case, you can use sine squared theta as half 1 minus cos 2 theta, and then you can do the integration. So what we have with that, you got 15 plus that one, I bring it down, 15 over 2, yeah, integrate 0 to 2 pi, we got 1 minus 2 cos 2 theta d theta. Now you can integrate those things easily. Okay, so what we have is 7 sine theta. That one you have 15 over 2 plus 15 over 2 theta. That one you have minus 15 over 2 over 2. This you got 2 down there, so you got half, so you got 15 over 4. Then give you sine 2 theta. Evaluate all these things from 0 to 2 pi. That give you 15 pi over 2. Okay, so this is the example of how to use the integral over the region using polar coordinates. So if you look at those region, where is it? Oh, over here. If you look at this region again, let's say you don't know how to, or you don't have the idea or how to transform that, yeah, in the exam, or that those ideas just couldn't come. You just integrate as normal. You can see how difficult it is. Yeah, this we have x squared plus y squared equal to 1. You can write this y equal to plus minus square root 1 minus x squared. Alright, for that you can write as we have x squared plus y squared equal to 4. That you can have y equal to plus minus square root 4 minus x squared. So if we integrate using a rectangular coordinate, so your integral would be you x from 1 to 2, okay, x from 1 to 2, but your integral now, you got negative and positive. If you consider the positive part, means just you only have that part. You consider the negative part, you only have that part. Oops, sorry. if you consider the positive, the limit positive, yeah, we have those. For the negative, we have those. So you need to consider both. Apart from that, the limit of integration is not easy to do. Yeah, so this y from 1 minus x squared, y to 4 minus x squared, those function you have 3x plus 4y squared dy dx, dy dx. And you need for the other side, so basically they are equal. Basically we have equal area from that and that, so you just can multiply by 2 without consider the negative part. You can just put 2 there. But to evaluate those integral is not easy. Yeah, it's not easy. You need once you integrate with respect to x, then you need to, I think you need to use the inverse sign to solve those integrals. So it's not easy as compared to the polar coordinate, so it's much more straightforward. Okay, let me give you one more example. If I have, yeah, I give you one more example. We find the volume find the volume of a solid bounded by plane z equal to 0 and the paraboloid z equal to 1 minus x squared minus y squared. So maybe you want to sketch how does those solid look like. Yeah. So in this case, because it involves z, you can consider a 3-dimension x, y, and z with a negative part as well, because we have negative part there. So with the negative part, so we just want the upper part of the of z, positive part of z. So we just left the negative. So what that does, z equal to 0 is a plane xy itself. Okay, z equal to 0 is plane xy, and those y equal to z equal to 1 minus x squared minus y squared. If you consider z equal to 0, if you consider z equal to 0, what you have for those, okay, if z equal to 0, we have exactly x squared plus y squared equal to 1. So this is a circle of radius 1. So we have this circle of radius 1. Okay, if you increase z, we have 1 minus and so on. So what we have is actually this kind of parabolic, that, because we have negative part there. So if you increase x and y, so what you can see is that the value of z become smaller and smaller. Okay, and x when x 0, y 0, you have this point here, z equal to 1. So basically that's your region or solid. So you can see at once here that since our integration on xy, we can map onto the circle, we can use a polar coordinates. So make sure you don't forget this thing, write down. We use polar coordinate. Okay, use polar coordinate. So this is the main point that you need to look at. So you have in mind that you're going to use the polar coordinate, and therefore you have x equal to r cos theta, y equal to r sin theta. What about dx dy? So d or dx dy is given as r dr d theta. Again, don't forget this thing. Okay, now for the volume, we integrate over those region. Let's call D. You can use D as a region R. Our function. Okay, our function. This is our surface here, given as z equal to 1 minus x squared minus y squared. So we have here 1 minus x squared minus y squared d dA. Remember that we use polar coordinates. So for the polar coordinates, so this is equal to, we integrate. Okay, so you can use theta from, this is, just look at the on the xy plane. You can transform this, or you can look at in xy plane, just xy plane. So what will happen, basically we look at from z positive, map onto that, so you have a region, a circular region there. So you have those, your region, okay, where x from 0 to 1 and theta from 0 to full circle 2 pi. Okay, so you have theta from 0 to 2 pi, r from 0 to 1, and then just substitute that 1 minus x squared is r squared cos squared theta minus r squared sine squared theta, and your dA is r dr d theta. So what you have inside there, the integrand, is that you have 1 minus get plus cos, you can cos sine, you take out r squared, so you have 1 minus r squared. Okay, and you have r, so everything you got 0 to 2 pi and r from 0 to 1, so we have r minus r cube dr d theta. And then you can evaluate those easily. That will give you integrate 0 to 2 pi, and that one you have r squared over 2 minus r squared over 4 r from 0 to 1 d theta. That give you integrate 0 to 2 pi, that you have half minus 1 over 4 d theta. Yeah? So this give you 1 over 4. Then integrate those 0 to 2 pi, 1 over 4 d theta. That give you 1 over 4 2 pi. That give you half pi. That's your solution. So you can see from here that the purpose of a polar coordinate is to simplify, or not really to simplify, but to make your work much easier. Yeah, much easier as compared to the we integrate directly on the Cartesian coordinate xy. Alright, so as a conclusion, what I have done in this video, that I explained, of course at the beginning of the lecture, that I explained the type 2 region. Then I'll go to the integration over the using polar coordinates, especially that region that involve we have a circular region, right? So for more general case of polar coordinates, I think just almost the same as this thing, so I don't to touch. I think I'm not going to go in detail on that. But in the next video, I'll talk on the change of variable in multiple integral, especially double integral. So with that, I think I'll stop here for this video. Bye.